Ignacio, thank you. Adrian. All right, so today we're going to continue talking about self-induction, mutual induction, and do a couple of exercises that were actually in the sheet of the previous section. Remember, I said they were out of place, right? So, and then you will see that they are actually very easy. And then we will talk about magnetic energy, actually about electromagnetic energy, and write the general expression for electromagnetic energy that we will have to use for pretty much the rest of your life. All right, as long as you are talking about electromagnetism. So let's just get going with that. And right, where is my presentation? Share. There it goes. By the way, I just uploaded like a few minutes ago this revised version of the presentation, including the couple of exercises that we'll do today. Okay, so you have it available in the virtual campus. Now, in summary, what did we do yesterday? And then, oh dear. Okay. Yes, sorry about that. The dogs basically think there is a party every single time I start some video conference. But anyway, hopefully they will not make a lot of noise. Anyway, so what did we do yesterday? Talking about mutual induction and also self-induction coefficients, right? In principle, what we said is that as long as in a given circuit, in an electric circuit or a loop, there is some current circulating that depends on time, and of course there is a magnetic field generated by the circuit that will also depend on time, induction effects can take place on the own circuit, I mean on the circuit itself, caused by its own variable magnetic field, okay? So we did define the self-induction coefficient, L, which is a very important coefficient, and I'll talk about it in a moment, as the derivative of the flux with respect to intensity. For most linear materials, the flux, as we discussed yesterday, is proportional to the intensity. So you can just calculate L as the quotient between the flux and the intensity itself, right? And this L is actually such an important quantity that for coils, solenoids, it is the equivalent as, to capacity for a capacitor. Remember the capacity, right? Just the usual quotient between the charge and the voltage that a capacitor can hold. Well, then, and then it was also very important to calculate the electrostatic energy stored in a charged capacitor. Well, L is going to be the equivalent for a coil. And we're going to talk about magnetic energy a bit later today, and you will see how actually equivalent the parameter is, and then also how parallel the equations become when one wants to calculate the magnetic energy stored in a coil, right? Anyhow, all this said, the actual EMF, electromotive force, right, induced in a circuit by caused by itself, it can be calculated as minus L times the derivative of the intensity with respect to time. And obviously, these effects are only important, as we discussed yesterday, when the intensity depends on time. So this typically happens when we are charging circuits or discharging circuits, for example. Anyhow, we did also talk about the mutual induction coefficient, which is basically how induction can be, let's say, established between two neighboring circuits when one of them has some intensity circulating through it that depends on time, and then maybe it's causing some variable magnetic field that is going across the neighbor. All right. So it basically, this is a coefficient that describes induction effects between neighboring circuits, and it depends just on the geometry and the way the system is built up, just like the self-induction coefficient. And we define the M21, for example, the induction effects on 2 caused by the variable field produced by 1 as the flux across 2 over the intensity in 1, which is the one causing the field across 2, okay? So just like it's a very, very similar definition, it's just that for the self-induction coefficient, one takes into account the flux across my own circuit divided by the intensity in the very same circuit. But for mutual induction, one thinks of the flux across the circuit one wants to calculate divided by the intensity of the primary circuit, the one actually generating the field, right? But other than that, they have, as you can see, very similar form and units and all of that. And then the induced electromotive force on circuit number 2 will also be written in a very similar form, like minus the coefficient times the rate of change of the intensity over time. Just in this case, the intensity is the intensity going through the primary circuit, not the secondary, which is what I'm calculating. Okay, but other than that, they are very similar. And as a matter of fact, at the very end of the day, if one wants to calculate the electromotive force and therefore the voltage induced and the current induced in any given circuit, for example, number 1, over here, one has to take into account both effects if they exist. The self-induced effects and then any effects caused by neighboring circuits. And of course, in this definition, I have actually included the mutual induction caused by number 2 on number 1. And in this case, I will have to obviously here put the intensity in number 2, assuming there is any intensity. And goes without saying, these are effects that must be taken into account when intensities and hence the resulting magnetic fields depend on time. All right. So like I said, this is typically during transients, during periods where things are changing over time, charges, discharges, and things like those. Okay. So like I said, let's just go and solve a couple of exercises from the previous section 5. We had 6, 7, and 8 pending. All right. So number 6 says that the space between two coaxial solenoids, so it's a system like this, of radii A and B and same length L, all right, much longer than A and B. In other words, we're talking about long coils. This is what we call solenoids, is filled with a magnetically linear insulating material of permeability mu. In other words, the system looks like this, but if we actually look at the cross section, so just rotate it 90 degrees, this is how it looks like. The inner solenoid of radius A is empty, and the outer solenoid is filled with a material mu that fills the space between A and B. All right. Anyhow, so if the number of turns of the solenoids are NA and NB respectively, find the coefficients of self-induction and mutual inductance, okay? And then we'll also find the magnetization currents in the magnetic material. And the data that they give us is, other than the number of turns, then the intensities along A and B. All right, so we have pretty much everything we need, and these are the dogs. Dogs, yeah, perros. Stop, vale, enough. Suficiente, perritos. Suficiente, por favor. I told you, there's a party here. See? There they go. Super party. Let's play. The rather, the better. I hope they will calm in a minute, and I definitely apologize because of any noise, okay? But if I actually put them in a different room, then they will start getting very upset and it will be worse. So please bear with them. Anyhow, like we said, let's just go and calculate the magnetic fluxes. This is the strategy that one needs to take into account every single time that we have a problem like this, because the coefficients are going to be flux over intensity. Just calculate the flux and then divide by the intensity, as easy as that. All right. So we will calculate the fluxes, and we will do this for the both solenoids. Solenoid A, solenoid coil A, right, on one side, and then coil B on the other one, right? So for the flux across the surface of solenoid A, right here, when there is an intensity going through A in the first place, and of course there is a NA number of turns, will be just the field caused by this intensity, right, BA, call it like that, times the number of coils and the surface of a single, let's say, section, SA. So this is going to be mu naught, because this solenoid is empty. N over L, we will use NA here, obviously, times IA. This is the magnetic field in A when there is an intensity, IA, going through it, right, times the number of turns and the surface, pi I square, A square, right, the radius square. So this is the flux going across solenoid A when there is an intensity IA going through it. And now let's do the same exercise for solenoid B. What if what we have now is an intensity IB going through solenoid B? Well, in this case, the flux is going to be a bit more complicated, but it's not so difficult. In this particular, we have to look at the cross-section of the whole system. And here we have a ring of, let's say, radii, internal radii A and external B, filled with the magnetic material. And then we have, of course, the internal section of radius A, which is empty. So what we have to say here is that the flux across my solenoid B, when there is an intensity IB going on the outside, right, is going to be the field caused by this intensity, B, times MB, the number of turns, surface of A, this is the empty part of it, plus the flux going across the section of the magnetic material, which will be B. But now we need to take into account the fact that this is a material, and we'll see in a moment how we do this, times MB, again, the number of turns, and then the surface of this section in pink, which will be the outer circle minus the inner circle, right, those two. So then the inner part is easy, mu naught MB over L IB. This is the field caused by the intensity called IB in here, times MB, and then the surface of this circle, right? We're calculating only for material, solenoid B here, plus, and here is where I say, oh, now we have to calculate the B, the magnetic field caused by the solenoid filled with the material of permeability mu, right? So then we put here a mu, and then same thing, N over L intensity, so this is the magnetic field B in the pink section, right, times pi MB, number of turns, and then here is B square minus H square, so we can actually get the section of this pink shaded region, all right? Now we have both fluxes independently, and we can calculate the self-inductant coefficients. And if anybody is thinking, right, because some sort of twisted mechanism, like, oh, why don't we have in here into account the fact that if there is also a magnetic field inside the solenoid A due to IA, all right? Batman, no te comas la silla, por favor. Che, no, eso no se hace. They like chewing on my furniture. Anyhow, so what, if you are thinking, why don't we add this to this flux? It's because to calculate self-induction coefficients, we only have to think that there is an intensity going across my own circuit of interest. For effects due to, Batman, stop it, no. Sorry, for any induction effect due to the neighboring circuit, in this case, the inner solenoid, then that's when we will calculate the mutual induction coefficient. So here we're only calculating flux independently, thinking there is an intensity going one, an intensity going through the other one, and then just stop it. Anyhow, so the self-induction coefficients for A will be the flux across A. Batman, que no. I am so sorry. You should see my living room. It's full. It's filled with furniture that is pretty much worth trash because of them. But anyway, they're dogs. Anyhow, LA will be the flux across A over the intensity that will go across solenoid A, IA. So just get this number here and divide by intensity. There we go. This is self-induction coefficient for A. And then for LB, same thing. The flux across B, this thing we calculated here, over the intensity that would go across B. And then it's a bit more complex, but this is just because the geometry of the system is changing. Notice that this is the self-induction coefficient for a single solenoid, right? Because if we're thinking of the inner system when there is nothing going on in the outside, we don't care because there is no field in the outside, right? So this is always the self-induction coefficient for a solenoid. And now this is a self-induction coefficient for a solenoid with two parts, one that is empty and one that is filled with a magnetic material. It's a bit more complex, but again, both of them only depend on the geometry of the system. You see here lengths, radii, right? And on the material, if there is any material, okay? So now, how about the mutual induction coefficients? Now is when we're going to take into account that we can have an intensity going on along both of them simultaneously. And so just for the purpose of completitude and understanding the system, we will calculate the what we would call MBA, in other words, the induction on B because of A, and then we will also calculate MAB, so the induction on A because of B. All right, and you have to see that they are the same. Remember, we discussed yesterday that mutual induction coefficients must be symmetric under the exchange of the point of view A, B, B, A. Same thing. It's just one system. So anyhow, let's think first of what would be the induction on the second solenoid B because of A. Imagine there was some current going through A, IA, right? And then let's think of what induction is going to happen outside. Well then, the induction will be basically the flux in the first place across the surface of B because of the field in A. Remember, there is only field inside A, right? The outside of solenoid A is not affected by the field caused by A. So the flux across the whole surface of B is only, you only need to take into account whatever is happening along the inner section, the circle of radius A. So here we have, there is the field, there is the surface. Oh, sorry, there is an NB, a number of I will fix this because it is important. So like I said, we are calculating the flux across solenoid B, and this flux depends on the number of turns of B. All right, so this is why I need to put the surface of A, because only in every circle of B, there is only a part of radius A filled with magnetic field. But then, of course, in this system, what we have to take into account is the number of turns that the system has, which is MB. Anyhow, so the field in A is mu naught NA over LIA. This is the field generated by the primary, let's say the inner solenoid. And then here we have MB times the surface, right? So now if I want to calculate the induction, the mutual induction coefficient, it will be this flux over the intensity of whom? Of the primary, the inducting circuit. This is A, so over IA, and this is what we get. All right, so we are here calculating the, again, mutual induction coefficient, in other words, the induction on the secondary circuit that for now me is circuit number B because of the primary circuit, which is A. This is why I put the flux across B due to A. All right, just like I said, for the sake of completitude, what if we also do the other way around and just calculate what would be the mutual induction if I just take the point of view of the primary circuit, the one of radius A, the inner one. In other words, what would happen if now I have an intensity IB circulating on this outer solenoid, and I wanted to see what kind of induction happens on solenoid A, the inner one. In other words, now the primary, the inductor, is the outside solenoid, and the secondary, the inducted, let's say, is the inner one, right? So now I need to calculate the flux across the surface of solenoid A because of the field generated by B. Let's call that flux AB. So that would be the field generated by B times the surface of A. Oh dear. Right now, right there. So now what happens? The field generated by B is going to be mu naught, because I am inside, okay? Material, the inner one is just radius A. Anyhow, MB over L, which is the field generated by the outside solenoid, times the surface of the inner one. And now I'm going to calculate the mutual induction coefficient on A because of B, putting the flux across A because of B, but now divided by the intensity of B, which is the inductor again. And surprise, surprise, I get the same result. All right, then. That's how you do things. And then the second part of the problem is quite easy. It's not difficult, but it's a good. Let's say, put up together everything. How about the magnetization currents in the magnetic material, right? Again, just on this donut, right, shape section. So just notice, but that the only field that the magnetic material is actually seeing is the field due to the outside. All right. the magnetic material is actually surrounding solenoid A, and the field, if any, generated by A is confined within the volume of A. There is no magnetic material there. So the magnetic material only fills the field generated by solenoid B. All right. So then the field H generated by solenoid B, if B is mu n over L I, H is n over L I, right? Without the mu. So this is it for B. It's a field that is going to be parallel to the axis. If we take the axis to be parallel to the x-axis, then we will just basically make things go along ux, right, the unit vector. And then in this particular case, the magnetic field obviously will be mu times h. It's one or the other, you can write it, they are equivalent, right? And I will actually put mu in here because we have a magnetic material of permeability equal to mu, right? So this is the field, one way or the other. Put h, put b. We need both because we need to calculate the magnetization. Okay, the magnetization inside the magnetic material will be B over mu naught minus H. So when you put these things together, this is what you get. And the interesting thing is that it's an homogeneous magnetization. And it couldn't be otherwise because the field is homogeneous and mu is homogeneous. The permeability here, right, does not depend on any spatial coordinate. So everything is going to be homogeneous. It's like a dielectric of homogeneous epsilon. Same idea. So anyhow, now that I have the magnetization, we can calculate the magnetization currents. The volume magnetization current will be the rotational of M, and that will be 0, right? And then the surface current will be M cross UN. UN is the normal vector pointing towards the outside, remember? So the only thing is that since we have two surfaces here, right, we need to take into account for the external surface when the radius is equal to B, that UN is the radial vector towards the outside of the system, and for the inner surface for radius equal to A, the normal vector is the radial vector pointing towards the center of the solenoid, just the usual. So if you take those into account, you are going to get for radius equal B and for radius equal A, two different plus and minus let's say, components of the surface magnetization current. One will go parallel to U phi and the other one will be anti-parallel to U phi. But other than that, they pretty much have a similar magnitude, okay, because M is homogeneous, and the only thing that changes here is the sign of the normal vector. So we have this distribution of magnetization currents that go, let's say, circular around the solenoid. I mean, around this pipe of magnetic material on one sense in the outside and a different sense on the inside, just like we plotted here. All right, no big deal. Now, second, exercise number 7 of our previous section. This is a similar one, but now instead of having two solenoids, we only have one solenoid, but filled with two magnetic materials. All right. It says through a solenoid of radius B and long length, L, much longer than B, and N turns, circulates an electric current I, right? So there is obviously going to be an homogeneous H field inside, right? The interior of the solenoid is completely filled with two magnetically linear insulating materials of permeabilities mu1 and mu2, respectively, and the first one occupies the space between 0 and A, so the inner, let's say, the core of the solenoid, and the second one fills the remaining space, so just like a pipe around it, right, between the radii of A and B, right? So something like what we have here, or this is the section, if you want to see it like that, right? So then we have to calculate the H, B, and M field through all space, the magnetization currents, and the coefficient of self-inductance of the system on itself. There is no two circuits here, only one, so we cannot calculate any mutual anything, just self-inductance. Now, one interesting thing that I want to notice again is that when we have solenoids, like in the previous exercise or in this one, and they are filled with an inhomogeneous system, like in the previous exercise or this one, that we have either one magnetic material and space and free space, or here we have two magnetic materials, just calculate with H. H is the equivalent of D, like we did in our let's say capacitor, remember? Then in this particular case, D would, for example, for a capacitor filled with the number of dielectrics, sometimes would be easier to reason in terms of that. Here we have H, which is, or B, actually, they are both parallel to the axis of the solenoid, right? And we have a symmetry of two different materials that also change like parallel to the axis of the solenoid, okay? So we have you say a revolution symmetry, right? Like that. There is symmetry also along Z, but there is not symmetry along R. So it's like having both materials. H is going to be the same in both. This is why we write H as N over L times the intensity. But B is not going to be the same in both. In material number 1, B will be mu A or mu 1 times H. In material number 2, B is going to be mu 2 times H. That's the thing you have to realize, that H is the same for both materials, B is not. Okay. Anyhow, so let's go for the fields. The one important thing, obviously, that everybody would realize in any case is that the fields are going to be parallel to the axis of the solenoid. You can take that to be Z, the Z-axis, so they are all parallel to UZ. And then H1 and H2 are the same, right? And then obviously N over L times the intensity. Okay. And the B1 in this case will be mu 1H, B2 will be mu 2H, and they are both parallel to UZ, right? So these are just their moduli. And then the magnetizations in both materials are going to be different because they have different permeabilities. In material number 1, the magnetization will be B1 over mu naught minus H. In material number 2 will be B2 over mu naught minus H. So it's not difficult to arrive to these expressions for both magnetizations. They are similar, but for this mu 1 over mu naught and mu 2 over mu naught. Same thing. All right, then. Magnetization currents, just like before. The magnetization current can be calculated on every surface by just multiplying M cross the normal vector. The only thing is that in the external surface, the normal vector is the radial vector pointing towards the outside of the solenoid, and in the inner surface, the UN in blue here is the normal vector pointing again towards the center of the solenoid. Nothing new there. Now, interesting, the one thing that we have to take into account is that radius equal B, where the normal vector is UR. It's not difficult to see that the product of UR cross M2, which is going like UZ, all right, UR across the other way around. UC cross UN goes like minus U5. So they're going to have a surface current that rotates again around the material, right? In one sense, in the azimuthal sense, so just like some contribution, right? Rotating around the axis of the solenoid on the outer surface where R equals B. But then in the surface between both materials, right there, we will have to take into account two contributions to the surface magnetization currents. The one coming from material number 1 and the one coming from material number 2. Okay, so material number 1 has a magnetization that is also parallel to UZ, so both M2 and M1 are parallel to UZ, but then depending on which one of both materials we want to calculate the surface contribution to the surface magnetization currents, UN is going to change sense. For material, let's say first the contribution for material number 2, UN pointing towards the outside will go pointing like that, like minus UR. But then for material number 1, the opposite thing would happen. For material number 1, the normal vector is going to be the radial vector pointing towards the outside. In other words, the opposite that I plotted here. I didn't want to plot all of them because they're going to be just complicated, right? But at the end of the day, when you do both, just like in a capacitor, when you had two, like a sandwich, right? Two dielectrics in contact with each other with a surface parallel to the capacitor plates, the polarization resulting charges on the surface were the subtraction of 1 minus 2. Well, same thing here, all right? So inside, there's going to be a distribution of currents that are going to be the superposition of M1 and M2. And in principle, I plotted things like on the outside, the currents go in one direction, like minus U5 if you want to see like that. And in the inside, maybe they can go just like that, depending on which is larger, M2 or M1. Actually, they could also end up rotating in the same direction that in the outside. It just depends on the relative magnitudes of the permeabilities, but we don't know about those. So this is just a sketch, but it doesn't have to be like that. Both surface currents could go in the same direction. That we don't know. That will depend on the relative sign of those two. Okay, but other than that, the calculation is similar to what happens in dielectrics with when we have capacitors, like hybrid systems, mixed systems. Okay. Last of all, the self-inductance coefficient. Well, again, calculate the flux and then divide it by the intensity. The flux across, this section is going to be a flux which is composed by two contributions. Whatever happens through material number 1 and whatever happens through material number 2. So this is what we have here. Through material number 1 with mu1, the flux is going to be field, B field, mu1 n over Li. Surface of 1, pi a square. Now, here is the contribution across the material number 2, mu2 n over L, same field, same H field, right? N over Li, and then pi, just B square minus A square, because that is the section of our external crown. So you put everything together and you get something like this. And then the self-induction coefficient, obviously, just divide this by I, and then you get this expression. And note again that it only depends on the material and the geometry of the system. It doesn't depend on anything like intensities, just like capacities did not depend on external parameters, just like the voltage between the plates of the capacitor. Only geometry and material, if there is any. Okay? All right. Last, exercise 8. This is a completely different exercise, and we have had a similar question in the exam of the last year or the year before. So it's a very interesting one, and this is going to be your homework for next week, okay? Maybe the last homework if I don't come up with anything else, right? So this is just the last thing you have to do for me, at least for the time being. Exercise 8 says a current intensity I flows through a circular loop of radius r, this one, capital R, which is parallel to and coaxial to another loop of radius A, but A is super tiny when compared to R. And there is another intensity circulating through the small loop, just this little I, and the distance between them is known. It's C. Calculate the coefficient of mutual induction between both of them. All right? All right. So this is going to be your homework due next Wednesday, January 20th. And actually, I want you to try do it in two ways. First of all, the easiest way, okay, is what if indeed A is super tiny, all right? And then when compared to capital R, of course. In this particular case, this is, actually A is always smaller than R, much smaller than R. So the tiny circle can always be considered as a magnetic dipole. That's a clue, okay? But anyhow, if this is super tiny, then here is the hint. You can just calculate the magnetic field generated by this circle here and assume it's constant over the whole surface. So the flux across this surface is very easy to calculate if you know the field of a circular spire, which you know. That is the easy way to calculate things. And now I also want you to calculate the precise way, the exact form of the coefficient and see that you arrive to something similar, maybe the same thing, all right? And in order to calculate the exact number, things can be complicated because if we don't assume that A is super tiny and the magnetic field generated by this large circle across the surface of the second circuit is homogeneous. If this is not the case anymore, now who calculates the flux of a non-homogeneous magnetic field across this tiny surface, or it might be difficult. The hint here, I should not say this, but I want just to give you the hint because there are a number of problems that have come up in exams that are similar to this one, is realize that if this is a dipole, I know the precise form for the magnetic vector potential of a dipole across this circuit. And the flux of this field across this surface is very easy to calculate with just with the circulation of this magnetic vector potential along this line. Because A, the magnetic vector potential caused by the small circuit along this big circle is constant on the whole thing. So ADL, I mean, the circulation of A along this thing is easy to calculate, and then you are going to get the exact value of the coefficient. So just do both, all right? I told you everything. All you have to do is go and do it, right? So, and then think about it. Just compare both results and see whether you get the same thing, that the mutual induction on this one is the same than the other one, and they're two different approximations. You see what happens. Anyway, this is due for next Wednesday. All right, for the last 10 minutes of the class, I want to talk real quick about magnetostatic energy, which is a very, it's not magnetostatic. Yeah, it is magnetostatic. We should just say electromagnetic energy here, because the result we're going to arrive to is actually general. It doesn't depend on whether things are static or non, okay? So, but anyhow, this is how the syllabus is put together, so I don't care. Anyway, electromagnetic energy here. And I'm going to talk about it real quick because it's actually the reasoning is very similar to the electric energy that we did for electrostatics. So, well, we'll see what we get to. The concept is that the magnetostatic, or in general electromagnetic energy stored in a magnetic system, is exactly the energy stored in the regions where a finite magnetic field exists. In this particular, is analogous to the concept of electrostatic energy that we saw in the past as the energy stored in the regions where an electrostatic field exists, right? The concept, how we're going to calculate this, is exactly the same than we did back then. How much energy does it take to build up the system? That is it, because this is the energy that somehow the system will be able to return at some point and give it back to me. All right. So the difference is just a matter of a concept, is that the electrostatic energy actually corresponds with an intuitive energy in the form of a potential energy, because there is the electrostatic field is conservative, there is a potential energy associated with the potential, and therefore it's sort of easy to understand. The magnetic energy is not associated with any kind of potential energy. So in this respect, it's an energy that is stored in the field. It's work that takes to build the field, but it's not any sort of conservative work or potential energy or anything like that. Other than that, so how do we actually calculate it? And it's important to know, because if a coil where there is an intensity I flowing has a constant field inside, there is an amount of energy stored in the coil. An inductor, a coil, stores magnetic energy just like a capacitor stores electrostatic energy. So what is the value of this energy? If we know the intensity going through the coil and also the self-induction coefficient, we'll see. Anyhow, the definition we're going after is that it is the energy associated with the magnetic field that can be understood as the work that takes to build the system. How do we build the system? It's a magnetic system, right? We have a coil. How do we build a magnetic system, a magnetic field up in a coil? Well, initially, imagine you have an empty coil, right? And then we have an external power source. We turn on a voltage. An intensity that initially was 0 starts ramping up until it reaches the final value I that we are aiming for. All right. So during this system of ramping up the intensity up to the final value, an intensity that depends on time is flowing through my coil. It's increasing from 0 to the final value, but during this transient, this period, the intensity depends on time, right? So the work that takes to cause this process to happen is going to be the magnetic energy that ends up stored in the system. And why does it take any work in the first place to build this charged solenoid? Does it take work, actually? Yes, of course it does. Because what happens, and this is what you have to realize, when you have this increasing intensity circulating to my coil due to the connection of an external battery or power source or power supply of any kind, right? We have an increasing magnetic field in the coil. The magnetic field is mu naught N over L times the intensity. If the intensity goes from 0 to a final value, the magnetic field is increasing along with the intensity. And if there is a magnetic field increasing across the surface of my coil, there is going to be a Faraday effect. The coil says, no, I don't want this coil. I don't want this magnetic field to increase. I want to stay like that. And there's going to be an induced electromagnetic force, an EMF, in the electromotive force, an EMF in the solenoid that produces a secondary field that wants to fight, in other words, opposes the increasing field. So the work that we have to make is exactly the opposite to this electromotive force that is induced because of the Faraday law as I increase the field with my external power supply. And it takes work to fight this reaction. Okay, this is what we're going to calculate. The magnetic energy is basically going to be the work made against this induced EMF per unit charge. Just like, in principle, electrostatic energies are potentials per unit charge, right? Voltage per unit charge, this is work. It has dimensions of energy. So this is how we are going to calculate the magnetic energy stored in the final field, right? Minus the electromotive force. Well, actually, energy per unit charge will be that, all right? So how do we calculate then? Well, the power that we have to use during this process will be the derivative of the energy with respect to time as usual. Now, if we can actually say that the magnetic energy is Q times epsilon, actually minus Q times epsilon, the derivative of Q times epsilon with respect to time, assuming, for example, that the pace of charging is constant, just for just the sake of simplicity, will be epsilon times the derivative of Q with respect to time, and this is the intensity. But then we know that if the self-induction coefficient of the coil is L, and we have already calculated now what is the value of L in the previous exercise for a coil, so we know this, then epsilon equals L, well, actually minus L times the derivative of I with respect to time. All right, so this is how we write the expression for the power that takes to charge the process. Li derivative of I with respect to time. Now, if we actually integrate with respect to time this expression, it's not difficult to see the integral of this with respect to time will be final energy minus initial energy. If the initial moment is t equals 0, there is no energy, so just total energy here. And then the integral with respect to time from 0 to final intensity of this thing is going to be 1/2 of Li squared, just what we have here. So the energy stored in an inductor where some constant intensity is circulating at the very end, I, is 1/2 of Li squared. And this reminds you a lot of things like what was the energy stored in a capacitor. Remember, it had a very, very similar form, just with capacities and voltages and so on. So the energy stored in an inductor that carries a current intensity I is stored in the magnetic field in the inductor. It's independent of time if the current is independent of time. So I'm talking about the final state of the system, and it only depends on the geometry and the intensity, because the intensity gives us the field and the geometry gives me the L. All right, and again, it's stored in the regions where B is not 0. Just like in a capacitor. Now, that is for a coil, but what would be the general expression for the magnetic energy that I was promising a few minutes ago? Well, in this particular case, let's just go back for a moment to the system where we have just some loop, right, C, which obviously defines a surface S, what's inside, right there. In this particular case, the flux across my surface, if there is some intensity circulating down the field could be calculated as L, the self-induction coefficient, times the intensity. And also, the flux is going to be, well, obviously the flux of the magnetic field or the circulation of the magnetic vector potential associated with this B along C. Now, if I make those two equal, I arrived into this expression, not difficult. And then, obviously, the magnetic energy that is from the previous slide, 1/2 of Li squared, can be written as 1/2 of Li, all of this thing here, times I. All right, I can put this intensity inside the integral because in principle it's the same for all of the curve, right? So it's like a constant. And then this is the expression of the magnetic energy in a circuit. And this is so looking like the electrostatic energy that was the 1/2 of the integral of Q times the potential. Remember, here we have intensity times the potential. And this is actually an interesting expression for you to have a feeling again of what is the magnetic vector potential associated with. It's like the electrostatic potential for magnetism, but of course, since there is no no conservative effect here, it's not really a potential energy of any kind, but it plays the very, very same role. Magnetic potential times intensity is just like in electrostatics, electrostatic potential times charge. So it's associated with the energy. And this is very, very important. You see a bit more about all of this in electromagnetism too. Now, this is the expression for a one-dimensional circuit. We can, of course, extend it to a three-dimensional system if you want to. And instead of having the line integral of A times I, one-dimensional intensity, we'll have a three-dimensional integral extended to the volume of whatever three-dimensional density of current is moving of A dot J, the current density. And I will not do a line integral, but a volume integral. And I'm going to use a small volume, a small v here for the volume. You'll see in a moment why I do this, right? So this is just the general expression of the magnetic energy. And again, you see here the role of the magnetic vector potential times current. Just like in electrostatic, we have potential times charge, right? But this is not actually useful for calculations. Let's go a bit further into this. Give me a couple more minutes, and then I can rewrite my J using the Ampere's law as the rotational of B over mu naught, right? Put that in there. I will use now the properties of the divergence of a vector product that, well, you have pretty much here the expression. So I can come into an expression where A dot the rotational of B can be written like B times the rotational of A, but this is B in magnetism. All right, so B dot B minus A cross B, put this into the equation, right? And now I arrived into this integral that has B squared, that's good, and then this divergence of A cross B, right? Using the Gauss theorem, I have here the volume integral of a divergence. So I can just evaluate the flux of A cross B over the surface that defines my volume, and now realize that my volume in principle can be infinite. This is like I can extend this. The magnetic integral is the integral containing the fields. The fields go to zero at infinity in principle, but in the meanwhile, they are actually extended typically to large volumes in the general case. So but since the fields go to zero at infinity over S prime, this product is going to be zero just by construction, right? If B prime is infinite, the surface contribution at infinity goes to zero because the fields are zero at infinity. So the only term that remains is this one. The magnetic energy is 1 over 2, over twice mu naught, the volume integral for all of space of B squared. So similar to our electrostatic energy, where the electric energy was epsilon naught halves the volume integral of B squared. Same thing. And as a matter of fact, what's inside the integral, B squared over 2 mu naught, is the energy stored in the magnetic field per unit volume. In other words, the density of magnetic energy, just like E squared times epsilon 0 over 2 was the density of electrostatic energy. So what's inside the integral, be it this one or my 1/2 of A dot J, is the energy per unit volume stored in the current density, which is where the magnetic field is defined. So in free space, in general, we had our electrostatic energy, like I said, that was charge times potential. This is why I'm using the small v here for the volume. For the magnetism, we have current dot the magnetic vector potential. And we have a very, very similar expression. The total energy, when we have both electric and magnetic fields, obviously will be the sum of both. And in the presence of materials, it's not difficult to see. You can look at this in any book. Just like the actual electric energy was from here, we just define D and say this 1/2 of D dot E. The magnetic energy is going to be 1/2 of B dot H. If we just make use of the fact that in free space, H is B over mu naught. But then, of course, for a material, it will be B over mu. All right? And that is pretty much where I wanted to arrive. See just the parallelism, the parallel expressions between both of them. They are not very different. And when we have both electric and magnetic fields, we'll have to sum both of them. Okay? They are pretty much the same thing. They are stored in the regions where we have a field, right? And the calculation is actually very similar. All right, then. Let me stop presenting, and this is the end of it. Tomorrow, we're going to talk about the next part of the syllabus, which will be magnetic forces and the displacement current. Actually, we're not going to talk about magnetic forces, but I'll explain tomorrow why. We'll talk about the displacement current, which is the only thing that we are missing to complete the Maxwell equations, okay? All right, then. I will see you tomorrow. Thank you, and bye.